Focus, in the most precise neuroscientific terms, is a neurochemical state one that emerges from specific, coordinated activity in the brain's attention and arousal systems. It is commonly believed that focus is purely a matter of willpower or mental discipline, but the biological reality is more intricate and deeply embedded in the physiology of the nervous system. To enter and maintain a peak focus state, your brain must reach a particular configuration where certain neuromodulators are active in the right quantities and in the right locations. These neuromodulators, specifically acetylcholine, norepinephrine, and dopamine, do not just support focus, they are essential for it. Acetylcholine is released from the basal forebrain and targets regions such as the prefrontal cortex and visual cortex, enhancing the brain's ability to select relevant stimuli while suppressing irrelevant information. It increases the signal-to-noise ratio in neural networks. What this means is that when acetylcholine is present, the brain becomes better at locking onto a task or input and ignoring distractions. It essentially creates a spotlight effect, emphasizing task-relevant information and downregulating peripheral noise. This process is particularly important in tasks that demand sustained visual or auditory attention, such as reading, writing, coding, or listening in a noisy environment. Norepinephrine, on the other hand, is produced primarily by the locus coeruleus, a small nucleus in the brainstem. It plays a critical role in alertness, vigilance, and the speed of neural signal transmission. When released, norepinephrine acts like a gas pedal for the brain, increasing the excitability of neurons and making the brain more responsive to incoming information. In a focused state, norepinephrine levels are elevated just enough to keep the brain highly alert, but not so high that the system becomes overwhelmed, which would lead to stress or cognitive rigidity. There's a sweet spot, sometimes referred to as the optimal arousal zone, where norepinephrine facilitates sustained attention without inducing fatigue or distraction. Dopamine adds a crucial motivational component to focus. This neuromodulator is synthesized in the ventral tegmental area, vita, and released into structures like the prefrontal cortex and striatum. It underpins the reward system of the brain and reinforces goal-directed behavior. When dopamine levels are elevated during a task, especially when the task aligns with an intrinsic goal, the brain interprets the work as rewarding. This creates a positive feedback loop where the act of focusing itself becomes reinforcing. Over time, this loop helps to build habits that support long-term attention and deep work. Importantly, dopamine doesn't just respond to rewards, it also anticipates them. When a person believes that effort will lead to a meaningful or satisfying outcome, dopamine increases in advance, enhancing cognitive engagement. These three neuromodulators do not operate in isolation. They interact dynamically to support the phases of focus initiation, maintenance, and completion. For instance, acetylcholine may be most prominent at the onset of a task when selective attention is required. Norepinephrine then maintains that alert state, while dopamine provides the drive to stay on task and see it through. This interdependent network is finely tuned and highly sensitive to internal states and external cues. Sleep deprivation, poor nutrition, lack of light exposure, or excessive stimulation can all disrupt the balance of these chemicals, making focus either short-lived or entirely inaccessible. This biological framework explains why certain behavioral protocols are so effective at enhancing focus. Exposure to bright natural light early in the day increases dopamine and cortisol in a healthy pattern, supporting alertness and mood. Movement, such as 20 to 30 minutes of aerobic exercise, increases baseline levels of both dopamine and norepinephrine, creating a neurochemical foundation for better focus. Likewise, deep breathing, especially exhalation-emphasized breathing, can modulate arousal through the parasympathetic nervous system, helping fine-tune the levels of norepinephrine and reducing hyperarousal that may impair attention. Additionally, mental framing and goal setting influence this neurochemical landscape. When individuals engage in tasks with a clear sense of purpose or intentionality, the brain interprets these signals as valuable, triggering the release of dopamine and acetylcholine. Internal motivation, therefore, is not abstract. It has a direct neurochemical correlate. Conversely, when goals are ambiguous or externally imposed without meaning, these systems don't activate with the same intensity, and focus tends to wane. This is why environments that encourage autonomy, clarity, and intrinsic motivation consistently outperform those driven purely by external pressure or unclear expectations. Understanding that focus is a neurochemical state also reframes how we think about distractions. Every time we switch tasks, get a notification, or scroll through a feed, we trigger small surges of dopamine. These rapid fluctuations can lead to dopamine deficit over time, which in turn makes it more difficult to sustain attention on less immediately rewarding tasks. In contrast, when focus is sustained, dopamine is released in a slow, tonic pattern that supports continued engagement without requiring constant novelty. This reinforces the importance of protecting focus time from interruptions, both digital and environmental, as each interruption can reset the neurochemical process and delay re-entry into a peak state. Visual focus plays a central role in determining the quality and depth of mental focus. This is not metaphorical, it is a reflection of how the visual and attentional systems in the brain are intertwined at the neurobiological level. The eyes are not simply passive receivers of visual input, they are actively engaged in regulating cognitive and autonomic states. Where we direct our gaze and how narrowly or broadly we focus our vision has a direct and measurable effect on how our brain allocates attention, prepares for cognitive work, and manages distractions. When we visually lock onto a single point, what is referred to as narrow or focal vision, the brain shifts into a mode optimized for task engagement. This action begins with the retina, where photoreceptors in the central region, the fovea, send high-resolution visual signals through the optic nerve to the brain's primary visual cortex. However, this is only part of the process. Simultaneously, narrow visual focus engages the frontal eye fields and superior colliculus regions that not only control eye movement, but are also deeply involved in attentional processing and top-down control. These systems work together to direct neural resources toward specific tasks while downregulating irrelevant or competing stimuli. The act of focusing your eyes tightly on a specific object triggers activity in the prefrontal cortex, the area responsible for executive function and attention regulation. At the same time, neuromodulators such as acetylcholine are released, particularly into the sensory cortex and the areas responsible for motor planning and decision-making. Acetylcholine sharpens the brain's signal-to-noise ratio, increasing sensitivity to relevant stimuli while reducing background interference. This chemical tuning enables deeper cognitive engagement. Importantly, this process is not solely dependent on what is seen, but how it is seen. Intentional narrow focus is the trigger. This interaction between visual attention and brain state also extends to subcortical structures like the locus coeruleus, which governs the release of norepinephrine, a neuromodulator associated with arousal and alertness. When visual attention is narrowed and held steadily, norepinephrine is released in a controlled, sustained manner, which elevates wakefulness and primes the brain to respond quickly and effectively. If attention is broken or scattered, often accompanied by rapid shifts in visual input, norepinephrine is released in unpredictable bursts that can lead to overarousal, anxiety, or a failure to maintain sustained attention. In this way, visual anchoring acts as a gatekeeper for mental focus. The act of staring at a fixed point isn't merely about stillness, it's about cueing the brain to enter a more concentrated state. For example, if you sit down to read and allow your eyes to wander around the room or constantly shift between screens, the brain remains in a kind of low-level search mode. But if you deliberately bring your gaze to the page or screen and hold it there, this tells the brain this is what matters now. That directive has biochemical consequences, particularly in the regulation of frontal and parietal attention networks. This mechanism also explains why moments of intense focus are often accompanied by stillness, not just of the body, but of the eyes. The reduction in eye movements corresponds with reduced activity in the brain's default mode network, a system that is active during mind wandering and self-referential thinking. By anchoring visual attention, you downregulate the default mode network and upregulate task-positive networks, increasing task performance and decreasing susceptibility to distraction. These effects have been confirmed in neuroimaging studies, which show that sustained eye fixation correlates with increased activation in brain regions responsible for working memory and cognitive control. Furthermore, visual anchoring allows for better coupling between visual input and motor output. In tasks requiring precision, such as writing, drawing, or typing, anchored visual attention facilitates more accurate and efficient execution. This is because the brain can synchronize visual feedback with fine motor actions more effectively when the visual effectively. It is also why elite performers in high-speed sports or skilled trades often train themselves to control their gaze before executing a movement. Their performance depends not only on physical skill, but on how well they manage the visual and cognitive precursors to that skill. Panoramic vision, in contrast, serves an entirely different physiological function. When the visual field is broad and unfocused, as in looking at the horizon or letting the eyes relax the brain shifts into a state of reduced alertness. This is accompanied by increased parasympathetic activity and decreased levels of norepinephrine and acetylcholine. While this is beneficial for relaxation, it is the opposite of what is required for peak focus. The transition between panoramic and narrow vision can therefore be used deliberately to shift mental states depending on the task at hand. The implication of all this is that the simple physical act of controlling your visual focus, where you look, how long you hold it, and how narrow your field of view is, has direct access to the mechanisms that determine how deeply you can concentrate. The connection between eye position and brain state is not abstract or theoretical. It is hardwired through multiple overlapping networks that bridge sensory input, cognitive control, and autonomic regulation. This makes visual anchoring one of the most accessible and immediate tools for enhancing focus without requiring complex interventions or external tools. The timing of when we attempt to focus matters as much as how we focus. This insight is grounded in neuroscience and chronobiology, the study of biological rhythms that govern fluctuations in brain and body function across the day. To enter a peak focus state, it's not just about willpower or eliminating distractions, it's about working with the natural timing mechanisms built into our nervous system. These timing mechanisms are governed primarily by circadian rhythms, which follow a roughly 24-hour cycle, and ultradian rhythms, which are shorter cycles that occur multiple times per day, typically lasting about 90 to 120 minutes. The circadian rhythm is orchestrated by a part of the brain known as the suprachiasmatic nucleus, SNN, located in the hypothalamus. This tiny cluster of neurons acts as the body's master clock, responding primarily to light exposure, especially the blue wavelengths present in natural sunlight, to regulate physiological and behavioral states. When light enters the eyes and reaches the SNN, it triggers a cascade of hormonal and neurochemical events that prepare the brain for alertness. Cortisol, the body's primary wakefulness hormone, rises sharply in the early part of the day, promoting alertness and readiness to engage with the world. This spike in cortisol is not a stress response, rather it is a healthy anticipatory signal to activate systems required for cognition and motor output. Within this broader circadian architecture, the brain also runs on ultradian rhythms, shorter cycles that influence alertness, focus, and performance capacity in more granular ways. These rhythms are characterized by alternating periods of heightened and reduced neural excitability, typically spanning 90-minute intervals. During the peak phase of an ultradian cycle, the brain is more capable of deep concentration, working memory, and problem solving. During the trough follows, cognitive and physiological resources are temporarily reduced, prompting a drop in focus and an increase in distractibility or fatigue. Recognizing and aligning with these cycles can dramatically improve the quality of mental work and reduce the perception of cognitive effort. The first ultradian peak usually begins about 90 minutes after waking, assuming a regular sleep schedule and proper exposure to morning light. This is often the most effective time to engage in demanding cognitive tasks, writing, studying, problem solving, or strategic planning. During this period, levels of dopamine, norepinephrine, and acetylcholine are elevated and well-balanced, providing the neurochemical conditions for intense focus and efficient learning. Neural networks involved in sustained attention, such as the dorsal attention network, are more synchronized, and regions like the prefrontal cortex exhibit greater coherence and reduced noise, making the mind more resistant to distraction. As the day progresses, subsequent ultradian cycles unfold with varying intensity. Most individuals experience between 4 to 6 ultradian peaks per day, though the strength of each peak can diminish if rest, nutrition, and light exposure are not properly managed. Each cycle contains a natural trough, a period where mental performance declines. Attempting to push through these valleys without rest or recovery leads to diminishing returns, increased mental fatigue, and greater likelihood of mistakes. This is where strategic breaks, ideally 10 to 20 minutes of rest, movement, or non-sleep deep rest, NSDR, can reset the system and prepare it for the next cycle. Aligning with these rhythms also requires recognizing how sleep and wakefulness impact neuromodulator availability. Sleep, particularly slow wave and REM sleep, restores the sensitivity of dopamine and norepinephrine receptors and clears out metabolic waste through the glymphatic system. A poor night of sleep doesn't just reduce alertness, it blunts the amplitude of both circadian and ultradian cycles the following day, making it harder to reach or sustain peak focus states. Conversely, consistent sleep and morning light exposure help reinforce a strong circadian signal, sharpening the transitions between states of rest and focus. Additionally, the circadian rhythm coordinates not only mental alertness, but also body temperature, blood pressure, and metabolism, all of which feed back into cognitive readiness. The brain tends to function optimally when core body temperature is rising, which corresponds to mid-morning through early afternoon. This temperature rhythm is also why many people feel a dip in alertness in the early afternoon, often referred to as the post-lunch dip. It's less about food and more about the circadian body clock temporarily reducing arousal before ramping back up later in the day. The science also shows that light and darkness exert powerful influence over these rhythms. Morning exposure to sunlight, ideally within 30 to 60 minutes of waking, helps set the timing of the cortisol pulse and anchors the circadian rhythm. This signal also indirectly affects the timing of melatonin release at night, ensuring that sleep occurs in alignment with biological readiness. Artificial light, especially late at night, disrupts these rhythms, delaying melatonin release and shifting the entire focus window forward, which can make early morning focus efforts feel sluggish or inaccessible. By observing and respecting these biological rhythms, individuals can structure their day to coincide with periods of maximum cognitive capacity. Attempting to force deep work during a trough or ignoring the signs of a cycle ending leads to wasted time and poor quality output. But by working in sync with these internal oscillations, the brain is more likely to enter and remain in a state of peak focus with less friction, less fatigue, and more consistency over time. Controlled stress, when deliberately applied and appropriately dosed, can significantly enhance focus by modulating the release of norepinephrine, a key neuromodulator produced by the locus coeruleus, a small nucleus in the brainstem. Norepinephrine plays a critical role in attention, alertness, arousal, and response to novel or challenging stimuli. It functions as both a neurotransmitter and hormone, and its release sets the tone for how the brain prioritizes information and suppresses distraction. Importantly, the relationship between norepinephrine and cognitive performance follows an inverted U-shaped curve, a concept well established in neuroscience where both too little and too much arousal degrade performance, but a moderate, well-regulated increase in norepinephrine can substantially improve attentional control and cognitive clarity. When the brain encounters a challenge or demand, the locus coeruleus responds by releasing norepinephrine throughout the cortex, particularly into the prefrontal cortex, which governs executive functions like working memory, decision-making, and top-down control of attention. This chemical signal boosts the activity of neurons involved in task-relevant processes while simultaneously dampening background noise and competing circuits. As a result, the brain becomes more selective about the information it processes. Attention narrows, distractions are filtered out more effectively, and cognitive resources are concentrated where they are most needed. This mechanism is evolutionarily adaptive. In a threatening or demanding situation, such as evading a predator or solving a survival-relevant problem, the brain's heightened arousal state increases the chances of a successful outcome. Modern neuroscience has translated this survival-oriented function into practical applications for cognitive performance. When managed intentionally, mild forms of stress can be leveraged to push the brain into heightened states of alertness and mental acuity without tipping anxiety or overwhelm. One of the most reliable ways to induce this beneficial form of stress is through deliberate physical discomfort. Short bouts of cold exposure, such as immersion in cold water or cold showers, activate the sympathetic nervous system and elevate norepinephrine levels dramatically by up to 200 to 300% in some cases. This spike in norepinephrine, while transient, leads to a sharpening of attention and increases the brain's readiness for focused cognitive effort. Similarly, high-intensity interval training, HIIT, or brief physical exertion can stimulate norepinephrine release. These physical stressors act on the body first, but ultimately shift the brain into a more alert, focused state that can be harnessed for tasks requiring concentration. Another powerful method for engaging controlled stress is time pressure. When a deadline is introduced or a timer is set on a task, norepinephrine levels increase, nudging the brain into a higher state of urgency and attention. This explains why people often experience sharper focus and better task completion rates under short, focused work intervals, such as the Pomodoro technique, which uses 25-minute work sprints. The temporal boundary serves as a mild stressor, activating the arousal systems just enough to push performance into a more efficient zone. However, the key is that these stressors must be perceived as manageable. When stress becomes too intense or prolonged, the same neurochemical systems that enhance focus can become dysregulated. Excessive norepinephrine can impair working memory, induce anxiety, and make the brain overly reactive. This is why the concept of controlled or hormetic stress, small, recoverable doses that lead to adaptation, is so critical. The brain thrives on challenge but falters under chaos. This distinction is encoded in how the autonomic nervous system balances sympathetic arousal and parasympathetic recovery. Interestingly, the individual's mindset about stress also influences how norepinephrine is utilized. Research has shown that when people interpret stress as enhancing or purposeful, they experience better cognitive performance and lower physiological costs. This is not a placebo effect. It is mediated by changes in how the brain modulates arousal. In essence, the framing of a stressful experience can determine whether norepinephrine acts as a performance-enhancing signal or a distractor. Cognitive reframing, then, is not just a psychological tool, it is a biological amplifier of focus-related neuromodulation. The timing and context of controlled stressors also matter. Deploying them just before a focus-demanding task can elevate norepinephrine levels precisely when needed. For example, using cold exposure or breathwork to increase arousal before a writing session or study block recovery can prime the brain for a sharper entry into the task. On the other hand, using these techniques too late in the day, especially close to sleep, can disrupt circadian wind-down processes, leading to fragmented sleep and impaired performance the following day. Thus, the strategic placement of arousal-inducing behaviors must be synchronized with broader biological rhythms. Another layer of nuance comes from the interaction between norepinephrine and dopamine, another key player in the focus system. While norepinephrine determines the degree of alertness and readiness to engage, dopamine governs the motivation to pursue and stay with a task. Controlled stress increases both, but in different regions of the brain. This synergistic activity reinforces the behavioral loop of goal-directed action, sustained attention, and eventual reward. When the brain learns that mild stress precedes heightened focus and successful recovery, completion, it begins to seek out that stressor as a tool rather than a threat. In summary, norepinephrine is a central switch for attentional tuning, and controlled stress is one of the most effective levers for accessing its benefits. By understanding and manipulating this mechanism, individuals can reliably enter heightened states of focus, not through brute force or avoidance of stress, but by skillfully engaging with it in ways that promote adaptation and cognitive precision. Goal-directed behavior is one of the most potent ways to engage and regulate the dopamine system in the brain. Dopamine is often misunderstood as merely a pleasure chemical, but its true role is far more nuanced and central to human cognition and performance. It is a recovery neuromodulator that signals motivation, drives persistence, and assigns value to outcomes based on the anticipation and pursuit of goals. In the context of peak focus states, dopamine functions as a biochemical engine that propels the brain toward task engagement and effortful action, especially when those actions are tied to personally meaningful outcomes. The primary regions involved in dopamine regulation include the ventral tegmental area, DIA, and the substantia nigra, two midbrain structures that send dopamine projections to various areas of the brain. One of the most important targets of these projections is the nucleus accumbens, a structure within the ventral striatum that acts as a kind of motivational gatekeeper. When a person sets a goal and begins working toward it, the vita releases dopamine into the nucleus accumbens and other cortical areas such as the prefrontal cortex. Recovery. This release is not a one-time event. Rather, dopamine is dynamically modulated based on progress, expectation, and perceived challenge. One of the core features of dopamine signaling is that it is anticipatory rather than purely reactive. The system ramps up in response to cues that signal a potential reward or meaningful outcome, often before any reward is achieved. This explains why even thinking about a challenging but worthwhile task can create a surge of internal motivation. The expectation of success or the belief that effort will produce a valuable result is sufficient to initiate the cascade of dopamine release that drives focus, persistence, and goal alignment. Interestingly, dopamine is also deeply involved in how the brain assigns salience or importance to stimuli. When engaged in a goal, dopamine helps filter out irrelevant information recovery and sharpens sensitivity to task-related cues. It shifts the attentional spotlight toward behaviors and choices that align with the intended outcome. This mechanism enables sustained focus, especially in the face of distractions or competing options. It also explains why tasks with no clear goal or payoff often feel tedious and difficult to engage with. Without a dopamine-driven signal indicating value or relevance, the brain struggles to maintain effort. As goal-directed behavior unfolds, dopamine release follows a feedback loop. When progress is made, even in small increments, the brain registers these micro-successes as positive prediction errors, meaning the outcome was better than expected. These moments of progress trigger additional dopamine release, reinforcing the behavior and increasing the likelihood of continued engagement. This process is foundational to reinforcement learning, where the recovery. Prefrontal cortex, where task rules, goals, and strategies are held online. Dopamine modulates the strength and stability of these representations, helping the brain stay aligned with the intended objective, even in the face of internal or external noise. This explains why individuals with higher baseline dopamine tone, or those who can effectively upregulate dopamine during effort, tend to exhibit better focus, self-regulation, and goal persistence. Importantly, dopamine is not merely tied to external rewards like money, grades, or recognition. It is equally responsive to internal goals such as learning, skill acquisition, or alignment with one's identity or purpose. When an individual frames a task as intrinsically valuable or self-congruent, the dopamine system is activated in similar ways as it would be by extrinsic incentives. This internalization of value is one of the key factors that distinguishes sustainable high performers from those who burn out. Motivation that is driven from within engages the dopamine system more reliably and over longer time scales. The dynamic nature of dopamine also means that it can be influenced and trained. Deliberately creating clarity around goals, reflecting on progress, and maintaining challenge at an appropriate level can all amplify dopaminergic engagement. Additionally, behaviors such as deep focus sessions, adequate sleep, nutrition, and time in natural light can support healthy dopamine tone and receptor sensitivity. Even mental visualization of successful progress can stimulate dopamine circuits, priming the brain for action. Goal-directed behavior is thus not just a psychological strategy, it is a neurochemical mechanism deeply embedded in the structure of the human brain. The dopamine system is the bridge between intention and action, and learning how to harness it through meaningful, measurable goals can transform the way the brain approaches focus, motivation, and long-term achievement. Non-sleep deep rest is a neurophysiological state that has garnered increasing attention for its ability to reset and enhance attention. It is a form of deep rest where the body and mind enter a state of relaxation that mimics certain aspects of sleep, but without actually falling asleep. NSTRA can be achieved through practices like yoga nidra or guided meditation, which encourage the relaxation of both the body and mind, facilitating a recovery process that promotes cognitive clarity, emotional regulation, and the ability to sustain attention. Understanding how NSTRA works requires exploring its impact on brain states, its role in managing stress, and its ability to reset the neurobiological systems that govern attention. The process begins with the body entering a state of deep relaxation. When engaged in NSTRA, the autonomic nervous system shifts from a state of high sympathetic activation, often characterized by stress and alertness, to a parasympathetic state. This transition is facilitated by a reduction in cortisol, the body's primary stress hormone, and an increase in acetylcholine, a neurotransmitter involved in parasympathetic relaxation. As the body and mind relax, the brain begins to downregulate higher frequency beta waves, which are associated with active, alert, and focused states, and instead increases alpha waves, which are linked to calm, relaxed attention and creativity. During NSTRA, there is also an increase in theta brainwaves, which are typically associated with light sleep and deep meditation. Theta waves are closely tied to a brain state that allows for deep, restorative processing of information. Research suggests that these waves play a crucial role in memory consolidation, emotional regulation, and creativity. As the brain enters this theta-dominant state, neural networks responsible for task engagement and cognitive flexibility experience a reprieve from constant processing, giving them the opportunity to reset and recharge. This resetting effect helps prevent cognitive overload and mental fatigue, conditions that can severely impair sustained attention and performance over time. The process of resetting through NSTRA has profound implications for focus. Attention is not a limitless resource. It is governed by neurochemical systems that need recovery periods to maintain peak performance. In particular, prolonged periods of focused work or high cognitive demand deplete resources in the prefrontal cortex, the brain region most associated with executive functions such as decision-making, working memory, and sustained attention. This depletion results in the phenomenon known as cognitive fatigue or decision fatigue, which can drastically reduce the quality and accuracy of decision-making. NSTRA, by allowing for deep relaxation, replenishes these depleted resources, rebalancing the systems responsible for attention and cognitive control. One of the key benefits of NSTRA is that it promotes a state of neuroplasticity. This refers to the brain's ability to reorganize itself by forming new neural connections. During deep rest, the brain is able to process and integrate experiences, memories, and information more effectively. By allowing for periods of rest where attention and energy are focused on internal states rather than external stimuli, Nstra helps the brain optimize its neural connections, making it more efficient at managing future cognitive demands. As a result, individuals can experience improved focus, memory retention, and problem-solving abilities after engaging in Nstra practices. Another benefit of Nstra in resetting attention comes from its impact on the stress response system. Chronic stress can impair cognitive performance by elevating the body's baseline levels of cortisol, which over time can damage the brain's hippocampus, the region responsible for memory and learning. By promoting a deep state of rest and relaxation, Nstra helps mitigate the effects of stress, reducing the harmful impacts of excessive cortisol, and enabling the brain to return to a more balanced state. This restorative effect is especially valuable in environments that require sustained attention, as it helps maintain cognitive performance without the need for continuous high-stakes effort. The practice of Nstra can also have lasting effects on the neurochemistry of attention. Research has demonstrated that regular deep rest and meditation practices increase the density of gray matter in regions of the brain associated with executive functions and attention regulation. This means that consistent use of Nstra not only enhances focus in the short term, but also fosters long-term improvements in cognitive flexibility, decision-making, and task execution. Over time, individuals who regularly practice Nstra can experience a more resilient attention system that is better equipped to handle distractions, stay on task, and recover from periods of intense mental effort. In addition, Nstra provides an accessible and efficient way to recover during the day. Unlike traditional forms of rest, such as napping, which can sometimes disrupt sleep cycles or leave, individuals feeling groggy, Nstra can be integrated into a busy schedule without compromising nighttime sleep. Even short sessions of deep rest lasting as little as 10 to 20 minutes can produce significant benefits for cognitive performance, making it a practical tool for anyone looking to optimize their attention throughout the day. The ability to use Nstra strategically, especially during the afternoon dip in cognitive energy, can help individuals maintain productivity and focus for longer periods without the need for excessive caffeine or other stimulants. Ultimately, the power of Nstra lies in its ability to facilitate a deep reset for the brain, particularly in relation to attention. By inducing a state of deep rest and relaxation, Nstra allows the brain to recover from cognitive strain, replenish neurochemical resource of focus, and restore focus. This state of recovery not only improves attention in the immediate term, but also enhances overall cognitive performance and emotional well-being. As such, Nstra represents a valuable tool for anyone looking to improve their capacity for sustained focus, resilience, and cognitive clarity in an increasingly demanding world. The relationship between physiological state and cognitive readiness is deeply interconnected. Our cognitive functions, such as attention, decision-making, memory, and problem-solving, do not operate in isolation from the body. Rather, they are influenced by the physiological state of the brain and body. The state of the autonomic nervous system, metabolic processes, hormonal fluctuations, and neurotransmitter activity all play critical roles in determining how readily the brain can engage in complex mental tasks. This interdependence underscores the fact that cognitive performance is not just a result of mental effort, but is intricately tied to the physical condition in which the brain operates at any given moment. The body's autonomic nervous system is divided into two branches: the sympathetic nervous system, SNES, and the parasympathetic nervous system, PNS. The SNES is often referred to as the fight or flight system, preparing the body for action in times of perceived threat or challenge by increasing heart rate, blood pressure, and releasing stress hormones like cortisol and adrenaline. These changes create a state of heightened arousal, which can sharpen attention and increase focus in the short term. When we are under stress or in a high-pressure situation, the body and brain are primed for heightened alertness, vigilance, and quick responses. However, while this heightened state of arousal is beneficial for immediate action, it can impair cognitive functions that require sustained focus, complex decision-making, and creativity, especially if the sympathetic activation is prolonged. On the other hand, the parasympathetic nervous system is responsible for the body's rest and digest responses. When the PNS is activated, the body enters a state of relaxation, slowing down heart rate and reducing blood pressure. This is the state the body returns to when there is no immediate danger or stressor, and it supports functions like digestion, tissue repair, and recovery. Importantly, this state is also essential for optimal cognitive function, especially for tasks that require concentration, deep thinking, and learning. The ability to switch between these states, the SNES for urgent responses and the PNS for recovery and focused attention, is fundamental to cognitive flexibility. The balance between these systems directly impacts cognitive readiness. Neurotransmitters, the chemical messengers of the brain, are critical to the regulation of cognitive states. For example, dopamine, often referred to as the motivation molecule, plays a crucial role in determining cognitive readiness. Dopamine levels influence attention, motivation, and reward-driven behavior. When dopamine is released in sufficient amounts, the brain is more primed to focus on goal-directed tasks. However, if dopamine is in a low state, cognitive effort becomes more challenging and motivation decreases, resulting in difficulty maintaining attention. Similarly, norepinephrine, another key neurotransmitter, plays a role in both cognitive performance and alertness. It is released in response to stress or novelty, and it helps enhance attention, focus, and the brain's ability to filter out irrelevant information. A certain level of norepinephrine is essential for peak focus, but too much, such as during periods of high anxiety or overstimulation, can lead to cognitive overload and reduced performance. This is where the concept of controlled stress, moderate, manageable levels of arousal that can enhance focus becomes important. Maintaining a physiological state where norepinephrine and dopamine are balanced is crucial for cognitive readiness. In addition to neurotransmitters, hormonal fluctuations play a pivotal role in shaping cognitive function. Cortisol, the primary stress hormone, is released during periods of stress and is essential for maintaining alertness. When cortisol levels are appropriate, they support the brain's ability to stay focused and respond to challenges. However, chronic or excessively high cortisol levels, as seen in chronic stress or burnout, impair memory formation and executive function. This is because prolonged cortisol release can damage the hippocampus, the brain region responsible for memory and learning. Cortisol's effects are also modulated by the circadian rhythm, as cortisol levels are naturally highest in the morning, preparing the body for the day's demands. This highlights how our cognitive readiness is not just influenced by mental effort, but by how well our physiological systems are aligned with our daily rhythm. Furthermore, nutrition and hydration play essential roles in cognitive readiness. The brain requires a steady supply of glucose to function optimally. Low blood sugar levels can result in difficulty concentrating, irritability, and a decrease in mental clarity. Similarly, dehydration can cause cognitive fog, impair short-term memory, and reduce attention span. Nutritional factors like the presence of omega-3 fatty acids, antioxidants, and other micronutrients are also important for maintaining brain health and cognitive function. Inadequate nutrition or poor dietary habits can contribute to suboptimal cognitive performance, making it harder for the brain to enter a state of readiness for focus. Sleep, too, is a key determinant of cognitive readiness. Sleep is not merely a passive state, it is an active process of restoration and consolidation. During deep sleep, the brain consolidates memories, cleanses itself of metabolic waste products, and resets neural networks responsible for attention and cognitive performance. Sleep deprivation disrupts all of these processes, leading to decreased alertness, slower reaction times, and impaired decision-making. This demonstrates the critical role that rest and recovery play in the brain's ability to enter a state of readiness. Individuals who have had a good night's sleep are far more likely to be able to focus and perform well on cognitively demanding tasks than those who are sleep deprived. The relationship between physiological state and cognitive readiness is further demonstrated in the concept of neuroplasticity, which is the brain's ability to reorganize itself and form new focus. Neural connections. Neuroplasticity is most active when the body is in a state of physical health and recovery. A well-regulated physiological state supports the brain's ability to learn new skills, consolidate memories, and adapt to new challenges. When the brain is overwhelmed by stress, poor sleep, or nutritional deficiencies, neuroplasticity is impaired and cognitive performance suffers. This highlights how physiological readiness is a prerequisite for optimal mental performance. Ultimately, cognitive readiness is not simply about mental willpower or the application of techniques to increase focus. It is deeply rooted in the state of the body's physiological systems, how well they are regulated, nourished, and aligned with natural rhythms. Understanding this intricate connection allows for more effective strategies to enhance focus, productivity, and mental clarity.